So in this video, I'm going to talk a little bit about subsets, complements, universes, as well as how we define sets. And let's start that as our main point of discussion here. So how do we define sets? There's two ways. The first way is through what's known as explicit notation. And what do we mean by explicit notation? What we mean is that we define a set by explicitly listing its elements. And we do this by writing the capital letter on the left-hand side of the equal sign. We open up a brace, and then we list our unique elements. Remember, they need to be unique, separated by commas. So this is the collection of numbers 1, 2, and 3. This is the collection of numbers, let's say 1, 5, and 4. And remember that if we write a collection that has a repeated element, it's just assumed that that element actually appears once. So we have to be very careful. And if there's some difference somehow between these two elements here, we need to make that explicitly known. The second way of defining a set is through the use of what's called set builder notation. And here's basically the idea. What we do is we say that a set is a collection of all elements X, where X can be anything, such that some statement P, which stands for proposition, about X, that's what the parentheses means. Some statement about X is true. So for example, I could say that the set B is the collection of all elements X such that X is prime. This, of course, would be the elements 2, 3, 5, 7, and so on out to infinity. This brings up an interesting point. Sets can be either finite, countable, or uncountable. And if they're either countable or uncountable, they are what's referred to as non-finite. Finite just simply means there's a fixed countable end of the set, meaning if given enough board space, I can write out every single element and be done. Non-finite means it goes out to infinity, but as we'll see later, there's actually more than one type of infinity, but I'm not getting into that right now. Now, it's just some notation. We say that an element X is in a set A. And we use this funny looking symbol, although I really butcher this bad. It really looks something like this. But you'll see me write this a lot. That's because I've just been doing that my whole life, and I apologize. But and some people do write it like that. This symbol just stands for in or is element. So for example, 4 is in the collection 1, 2, and 4. Why? Because 4 is an element of this set. So if we write the statement I is in the set A, we're saying that some variable I is equal to some element that's in A. For example, I could consider the collection of all trucks, where I have truck 1, truck 2, and truck 3. If I make the statement J is in the set T, then I know that J is equal to T1, or J is equal to T2, or J is equal to T3. Do I know which one? No. So when I write this statement generically, all I'm just saying is J is a variable where it's going to be set equal to one of the elements in the set. I don't know which one, but I know that it's somewhere in this set. Now, usually when we talk about sets, we have the concept of universes. So a universe is a collection of all elements under consideration. For example, I could consider the collection of all trucks in my company, where let's suppose I have 50 of them, and I label them T1, T2. Sometimes you'll see me use this notation, comma, dot, dot, dot. That means I'm exhibiting a pattern, right? T1, T2, T3, and I'm going to keep going in this, T4, T5, etc., up to T50. So that's all the dot, dot, dot means. So my universe are all trucks. If I think of my universe as a box, then I have T1, T2, T3, T4, T5, right? And I have ten of these going in, multiple directions here. Like this, like this, like this, like that, right? So I fit my 50 trucks. That's my universe. As it turns out, I can construct sets from other sets. So let's consider one set. Let's suppose these sets right here. And suppose I've labeled these T1, T2, T3, T4, T5, T6, so on and so forth. So consider the set T, where I have T1, T2, T3, T4, and T5, separated by commas. Forget the 3 should be a subscript there. So that's what the set T is right now. As it turns out, I can construct a new set by looking at the opposite, meaning this is the collection of all elements X that are in the collection U, meaning my universe, meaning all the elements in my box, such that X is not, when we write a line through that funny looking E, that means it's not an element of T. And so when we look at that, those are all of these elements right here. And when we have that, usually we write it as TC, but sometimes you'll see authors write this as T prime. Either one works. So TC, T prime, that it refers to what's called the complement of a set. In this case, it would be defined as T6 all the way up to T50. Okay, last, and we've sort of hinted at this idea, we have the concept of a subset. A subset is a collection whose elements are part of a different set. Put differently, if we have two sets, set A and set B, and all of the elements A are contained in B, then we say that A is a subset of B. If there's an element in B that is not in A, then we say that A is a proper subset of B. So for example, if I have the set A equals 1, 2, 3, and 4, and I have the set B is equal to 0, 1, 2, 3, 4, 5, then A is a proper subset of B. The reason is that I have elements, more specifically 0 and 5, which are not in B. By the way, we also have what's called set difference, which if I do B minus A, this is just the collection of all elements of B such that that vertical line here means such that X is not in A. And in this case, that would just be 0 and 5. Pretty straightforward stuff, right? So those are the basic concepts of sets, subsets, set notation builder versus explicit notation, universes, and complements. By the way, in this example, B can be considered a universe. And so if we write a complement in this case would be 0, 5. The reason we can consider B a universe is because A is completely contained in B. However, if I had the sets A equals 1 and 3, and B is equal to 1 and 2, then A is not a subset of B. And we typically write this. The reason is because 3 is not in B, and 2 is not in A. So 1 is not a subset of the other. One last thing to mention in this video is that two sets are equal to each other if and only if A is a subset of B and B is a subset of A. If this is true, then the two sets are equal to each other. So one way of showing that two collections are the same is to first show that one collection is completely contained in the other, and then going the opposite way by showing that the other set is contained in the other. When both of these are true, the two sets need to be equal to each other. The last set, which I forgot to mention, is the null, otherwise known as the empty set. We usually denote this by this funny looking 0 here. And this is just the collection of nothing. It contains no elements whatsoever. So those are the basics of sets. We'll get into some set operations in the next video.